Yes, yeah. So I'll give you an update on the oLIVER project, which is been also running here for 1.5 years almost, and it is going to be about how we find biomarkers for liver diseases, in particular like NASH and other fatty liver diseases we are interested in. And this is a joint collaboration between the clinical people here, which is where we have Henning Grønbæk, who's providing many of the clinical samples. And we also have mice provided by Christian Vector. And then we are kind of processing look into the biomarkers of the blood of these individuals. And then we are collaborating with the Novo Nordisk company, who's very much interested in finding biomarkers for these diseases, both as a potential way of following these patients, but also maybe as a potential targets in the future. So just a little short recap of the method that we are applying in this. It's kind of a novel method that we have developed over the last 3 or 4 years in our lab. And this is like making a huge library of RNA molecules. It's actually 10 to the 15th molecule, so it's a large amount. And these fold up in small structures and will interact with proteins in the blood. And we can separate the ones that bind from the ones that do not bind. And in a little, you can see here how it works. So the RNA will fold up in a structure. Some of them, a very few of them, will fold up and actually interact with the proteins. And those are the ones that we recover. And a little bit simplified, I'm not going to go into the whole details. We actually then can sequence these bound RNA molecules and interpret them using machine learning programs. And we can get these molecules to recognize deceased patient from healthy and other conditions as well. Because these are RNA, we can actually separate the ones that are best to recognize the disease, and we can synthesize them and put them on magnetic beads, and then we can then pull down the proteins and use mass spectrometry to analyze the protein. So this is the workflow we call AbsoShape, and this is the one that we applied to clinical samples and mouse blood samples in this project. So the result looks like this. This is, in fact, on mouse blood provided by Novo Nordisk. This is, I'm showing you because we also done now the human samples, but these are just being processed. So we are still in the midst of kind of having the final results there. So here you can see how it works, that these mice, in this case, is either fed by a lean diet that we call chow, or they get a Western diet where they get really fat and get diabetes. And these are mice that are genetically manipulated, so they do get very sick from being fat. And then they are treated with 2 compounds from Novo Nordisk, and of course Novo Nordisk is interested in finding out what these compounds do to this disease. And you can quickly see here already that we have a whole lot of aptamers that can kind of recognize the lean mouse blood from the Western mouse. And you can also see that some of these drugs actually pushes the signal towards the lean mice. So we are taking usually about 1,000 different aptamers out, and then we use these to provide maps of how the mice are changing in the blood. And this is what we call a PCA plot. These are the 1,000 top sequences that we use. And you can see here that the control or the lean mice is up here, the red ones, the Western diet ones are down here. And then when we treat it with these compounds from Novo Nordisk, they are moving away from the heavy mice, but not really up to the lean mice. So this is, of course, interesting to now dig into what proteins they are. And we have done this, and I'm not going to go through the data here, but this is, in fact, what we exactly are doing on the patient samples as well. So this is a little boring slide. I just want to mention that we have done all the data or the clinical sample collections with Henning Grønbæk group out there, and also we have got it from Christian Vector, the blood from the mice, and we have done most of these AbsoShape analysis. We also are using a robotic platform now, which we learned from the Novo Nordisk how to really use these quick robots, and that has been a big help. And we also have started to modify our aptamers with some chemistry. So we actually got a proof of concept that they can be modified now, and we will expect them to be even better to recognize proteins than without these chemical modifications in them. And yeah, so we are in progress doing these cohorts. We have got all the data and now analyzing them. And then we also have a project that we still need to do is to compare blood from people that undergo surgery and compare them to the GLP-1 analog treatment. And that will come up. And the rest of it is kind of more trivial things. So I also want to just share a couple of thoughts about these ODIN projects. I would say that just as the former speakers mentioned, it's much easier with the legal considerations. We don't need NDAs or CAs. They are all kind of filed in advance. And also, we don't have to spend time thinking about intellectual property filing because you cannot do. We all, let all our data out there. And also, there's no economic ties between the company and academia, which is actually nice. We can collaborate without, having to ask for money because the money is provided by the ODIN project, and that actually is a big help and is more mutually satisfying for both company and the academic group, I would say. There's also a few cons. There is a risk, of course, that you are sharing unprotected IP. You always have to kind of ask the company to make sure that you are not doing something wrong because you let everything out there. And also the GDPR agreements is not kind of completely built into the ODIN projects yet. And it has taken us actually a long time to get all these agreements in place. So this is something we might have to look into. There's also somehow a need for a system for sharing the data. We have no ODIN secretary have been secretaries have been talking about how to do this, but I think we have to at one point solve exactly what type of data we should share, because there's no room for all the data, because we have gigabytes, many gigabytes of data, and somehow we have to curate these data and put them out there, because otherwise they will be meaningless to the people. So we have to decide exactly how to present our data and how much we should put out there. I also just want to mention that I think there's a huge potential with this method here. It can be applied to any biofluid. And it actually have helped us, this ODIN project, to really put it up into this high-speed method with the robots. So we can actually look at a lot of different diseases now. And we also started to look at other things than blood. We have a collaboration now with ALA, where we look at milk, and we can identify the components in the milk that are influencing the cheese production, which we'll look more into. So I think it's an example of how you can spread to different applications very quickly if you have a good foundation with a very good fast throughput pipeline. And an example of something that could be taken out into a more IP protected. I mean, this is one of the ideas, of course, with ODIN, that you should try to see what you can spin out and actually use more in a protected environment. And one of these are that we actually started to use these Oxford nanopores to read our aptamers. And we have a kind of a new way of doing this that I'm not showing you here, of course, today, but we think that we can actually build up aptamers that are kind of disease specific, and then we can, using these nanopore sequences, actually get a very quickly diagnose from the blood, for instance, on what type of viral infections you have. So that is something that we would like to spin out and see whether we can do some more closed research on.